Shall we start now, sir? Hello, sir. Hello, sir. Hello.
Am I audible?
Yes, sir.
Okay, madam. You can start.
Okay. Hello, everyone. Present here virtually. I am Preeti here, and I have welcomed you all for today's session, which is titled as Development and Characterization of Functionally Graded Material. And presenting this session, we have with us our today's expert, Dr. Srinivas sir. Dr. Srinivas sir is an associate professor, Department of Mechanical Engineering, Vardhaman College of Engineering, Hyderabad. His qualification is PhD Manufacturing in JNTUK, Kakinda. Has 16 years of teaching experience and 4-year industrial experience. He has done extensive research in symposites, functionally composites, and metal matrix composites. He has 18 international and 4 national journal publications. He has research project under SERB of worth 16 lakh. Without wasting much time, I have welcome you, Dr. Srinivas sir. You may start now, sir. Hello, sir.
Shall I start it, or should I wait for the participants?
You start, sir. Participant will join in live session.
Okay, madam, definitely. Okay. Good afternoon, one and all. This is Dr. PNS Srinivas, working as an associate professor in Department of Mechanical Engineering, Vardhaman College of Engineering, Hyderabad. So today my topic is development and characterization of functional graded materials. This functional graded materials is an advanced material, so which is extensively used only in the research applications. It is not very well developed. Why? Because due to its limitations in the manufacturing as well as in the characterization process. And also it is very difficult to develop. Only some of the countries are using it. Only in India we have the basic research of functional graded material. So in the functional graded material, why the selection of the materials has been designated as the functional graded material? So itself it suggests that, or itself stands for a material which can be applied only due to its functionalities. And according to it, it is gradation in the volume side. So means according to the functionality. Means suppose if you want for a mechanical characterization or mechanical extensive mechanical characterization or mechanical applications, we can do as per that functionality. If you want to change for a microstructural characterization or microstructural applications, we can change in that manner. Or we can change in the combination of mechanical, microstructural, tribological, and all other parameters. So that is a vast variety of applications can be equipped in a single material, and hence it is called as functionally graded material. So my topic consisting of these things. So I have removed that abstract, and from the introduction, and next is the previous researchers, what we have done in the literature, or what are the studies done on the functional graded materials, and how I choose my materials, and what is the manufacturing methodology I have adopted, and what are the tests I have done, what is the characterization techniques I have done, and results and discussions. And afterwards, the questionnaires, so the question time or the queries. So comes under the functional graded materials. So functional graded materials are those materials. So it is an advanced engineering material. So that is able to survive in very extensive working conditions. So that it could be in high temperature, or it could be having a low temperature, or it could be having a combination of or a cyclic temperature, or it could be having a fatigue stress or a cyclic stresses. Without if you have n number of stresses and n number of strains, without having change in the metal properties, it will be having a service life. So that is why it is an extensive material. So it is applied in the aeronautical as well as the present ongoing research of the automobile applications. And these are considered to be heterogeneous. Why? Because in the same material we are having the base material as one compound and the reinforcement, just like a metal matrix composite. But in the metal matrix composite, you have a uniform dispersion of the materials. So that is the even though the metal matrix composite are what you consider as the heterogeneous, but if you take at each and every point of the product, we will have the same metal properties. But if you take in the functional graded material, the functional graded materials, as we proceed from the bottom layer to the top layer, or top layer to the bottom layer, there will be a progressive change in the metal properties. Either it could be increase of the compression strength or decrease of the compression strength, increase of the tensile strength or decrease of the tensile strength. Means we can able to vary our properties at any point of our metal composition. So that's why these are an advanced material. So this is not the new metal we are using, or it is available in natural. So in the nature it is available. So just like the wood, our teeth, and different kinds of muscles, we are having this functional grade materials. But the research has been not done. So we are mainly focusing on alloys and composites and metal matrix composite, polymer reinforced composites, glass reinforcement composite, and all other types. But this kind of research is an important research. So where we can have extensive properties. So if you observe the material, so this is the schematic diagram of the functional graded material. In this functional graded material, we have 1, 2, 3, 4, 5 phases, right? Or we can have 3 phases. So this is nothing but the metallic phase, and this is the transition phase, and this is the ceramic phase. So metallic phase, why you have called it, means basically the matrix metal is treated as the matrix metal is treated as the base metal. So matrix metal is treated as the base metal. So metals will take just like as aluminum and aluminum alloys, copper alloys, tungsten alloys, vanadium, uh, and all kind of nickel, carbon, and all kind of things, all kind of metals we can take in the metallic phase. And then when we proceed further, means if you take here, if you take the blue, if you take the black part, that is what is called the metallic phase. That is the pure metal. Suppose if you take an aluminum, pure aluminum, that is the black one is indicating the pure aluminum. Then the white spots will be indicating when there are reinforcements such as ceramic inclusions. And when we proceed further and further, and when we reach the topmost phase, we will be only having the ceramic phase, right? So the ceramic phase is nothing but the reinforcement phase. So in between, when there is a metallic matrix, that is the matrix metal, that is what is called as the base metal. When we have the maximum material, what we take, so that is the maximum composition of the material, that is what is called as a matrix material. So that will be having most of the thing, that is what is called as the metallic matrix. Then when the reinforcement, that is where the reinforcement we are using the ceramics, just such as we can use silicon carbide, titanium carbide, magnesium carbide, and all kind of things. When we use that ceramics, that it becomes due to the metal properties, we will be using that ceramic inclusions. And then next, the transition region. The transition region is nothing but the region where there is an equal distribution of the matrix as well as the ceramic one. And when you go on another phase, when there will be increase of the ceramic, so then the ceramic phase increases, that is ceramic percentage increases, and then the metallic inclusions decreases. And in the topmost region, we only have the ceramic phase, right? So when you see in a wood material, so the wood material also will be having like, so the topmost one or the outer layer. Outer layer will be only having the what you called as cork, or it is the hardest material or the hardest looking surface. When we proceed further, so we'll have an what you call in the brown color, the green color, and also other things. So when you proceed further or you go getting into deeper, so then the strength or the hardness of the material will be decreased, right? But we don't, even though the wood is cut, we will be only considering the a layered wise, means we will be taking the third or fourth layer. Why? Because we want to have a smooth finish rather than having, even though how harder the material at the outside, we will only consider where there is a surface property. Why? Because the surface finish should be good. Otherwise, we cannot able to have our furniture, right? So that's why we'll be only using this. See, this is a layer wise deposition, this is a layer wise. So here this is a natural wise. So in the by this is an inspiration by which I will be considering as this is the metal by which I want to prepare this kind of metal, means the metal will be having this kind of layer depositions, right? So here this will be the hardest material will be the matrix material, and when we proceed, so this will be your ceramic inclusion, that is the reinforcement inclusion. So this is also one of the schematic one. So this is the material one, material A, transition A, that is nothing but the matrix material, and material B is nothing but the ceramic or the reinforcement one. So totally the reinforcement, when there is a reinforcement one, there will when an ultimate reinforcement one is done, there will be no matrix material. This is a transition region, there is a mixture of matrix as well as the what is called as a reinforcement. And due to this, it is an have become an advanced material by which we have a variation of the properties in the volume gradients, right? Then it is also an unique and an advanced when compared to all other materials, such as alloys and composites. So this is then other things, so such as your bones and teeth. So here, if you take the first one, this is the composites. If you take a polymer composites or a metal matrix composite, there will be a uniform distribution of the metal properties. But when you take a functional graded material, so functional graded material will be having a rise of metal properties or a lower of the metal properties as you proceed from the bottom to top or top to bottom. So actually, the research has been done in the origin of this functional graded materials is done in 1984, when a space rocket from the Japan has been traveled into the outermost orbital. And while after doing the space research, either it could be on moon or it could be on any planet. So maximum they have done a research at there, and they have collected the samples, and then while returning to the earth, what happened means, due to the severe temperature, so due to the severe thermal gradient what is happening at the outermost orbital, and due to the failure of the fuselage, the sudden fuselage breakage, so total entire 19 astronauts have died. So that made that is a biggest failure of the space research, which is developed by JAXA, that is Japan Aeronautical Space Research, aeronautical applications. Then they have been extensive. Then from that time on, they have been extensively researching this kind of products, and mainly for the aerospace industries and aircraft industries, they have developed these materials. And later on, they are being now we are switching into the microprocessors in automobile applications and domestic applications. So this is also in terms of the weight proportions. So from bottom, we will be having 100% of the matrix material, and from the as we proceed top, we have 10% of the reinforcement, 90% of the matrix material, and we proceed forward and upward. So we will be having 100% of the reinforcement. So this is the graph showing the material gradation, that is the material composition, and the B side, that is nothing but uh, the composite material. So these are the evaluation of the evaluation of the metal properties. So that is evaluation of the metals. So from pure metals, non-metals, then we have been generated the alloys, and from the alloys we have developed the composites. And next, we have not only the composites, we have smart materials, shape memory alloys, and afterwards we have been discussing the advanced materials, function graded materials. So this skin is also one of the examples of the function graded materials. So the trees, so already we have discussed. So this is the literature review. So literature review, and I have taken the latest one, 2019. So Saleh and Ahmad, so they have been done research on the function graded tubes, of which aluminum is taken as the matrix material and alumina is taken as the reinforcement. They have been generated by using the centrifugal casting for automotive applications. So that is published in Metallurgical and International. Hello. Metallurgical and Materials International 2019. And here, in why he has chosen centrifugal casting means the centrifugal casting is an widely used process in preparation of alloy materials, where we can able to cast a product by using centrifugal force, and the tubes are produced, and he has checked the tensile strength, hardness at the inner and outer zones, and also find out the weight test by using the tribological weight test apparatus, and found that the surface wear at three different loads, mainly at 5 newtons, 10 newtons, and 15 newtons. And he has, due to the microstructural characterization, he has seen that there are visualization of some cracks, delamination, and some kinds of deformities. But in this research, by taking the centrifugal casting, there should be a gradation of the metal properties. And in this research, there is a research gap of how could there be a gradation of the metal properties when we move from the layer wise, or there is no significant visualization of the matrix and the reinforcement, either they are bonded together or not, and there is a gradation of the metal properties are not exclusively discussed. So this is one of the these are 2 to 3 gaps, research gaps found out by analyzing this paper. And similarly, by using magnesium modified hypereutectic functional graded aluminum composites, even though there is a wear analysis of it, and he has taken here, Jai Kumar has taken the base metal as A390, so one of the aluminum alloys, and he has taken magnesium. Magnesium is a very brittle material, very susceptible to brittle, and it is susceptible to heat also. And he has taken magnesium to have a magnesium composite, and thereby he has they have taken a percentage of 2 and 4, and he has checked the wear and microstructure properties, and he had said that wear properties have been advanced or enhanced significantly. But the manufacturing of here also he has taken the centrifugal casting, but the validation of the process is not very discussed in an extensive manner. And also it is having when you observe the microstructure characterization, there is a more amount of what you call the debris and the deformities rather than low, and also porosity is also not discussed. So porosity is also plays a vital role in the microstructural characterization. Then only we can say that they have been, and the EDX and the XID analysis are also missing. Only has done the wear analysis, and in the wear analysis also he has increased the magnesium to 2 and 4 percentage, and he has not taken higher amount of the magnesium, and the speeds, the loads are given, but he has not discussed the speeds. So the speed is also playing a vital role in finding out the wear characterization. So the wear characterization is mostly depending upon the load what is acting and the speed of the wear rate, and the also the time. So the three process parameters are to be extensively discussed. So these three parameters are not been extensively discussed. That is what I found out in this literature. And also like this, there are so many of research has been done from so past a decade. Now, so I have also segregated in terms of is this is a research paper, or is this a review paper, or it is just a comparison paper, like this. So after going through all these things, the research gaps what I found out means, so even some of the researchers have done the powder metallurgy process, but the extensive systematic procedure to develop the functional graded metals by using powder metallurgy has not been discussed very well, and also the process parameters also not very well discussed. Next, the blending process. The blending process is an important one where we mix the matrix as well as the reinforcement, or not done as per ASTM, that is American Society for Testing Materials. So that ASTM will have the specified standards. So thereby we need to mix the materials. We need to mix the material as per as the rule of mixtures. And also by using ball milling operation, we need to blend our materials and to an required proposition. So that is also not very well discussed in the previous research. And the compaction and ejection process, that is what is done through the powder metallurgical process, that is in the CTM, that is the compression testing machine. So that in the compression testing machine we will be using as the compaction process. And here the loading conditions, that is the what is an eject compaction load and ejection load. Simply they have in the previous research they have given the material is produced, but how much load is applied, and how much time is applied, and what is the dwell time, what is an ejection process, and what are the process parameters, they need to be optimized. Why? Because this is an experimental process. There are more process parameters are involved. That is optimization. Optimization process should be extensively discussed. When this optimization, when there is no consideration of the optimization, then ultimately failure of the metal will happen. So then ultimately the wastage will be done. So the wastage, in order to nullify the wastage or to decrease the wastage, we need to optimize the process parameter. That is a very important process while considering any experimentation process. So, and also I have gone through other conditions such as the centering temperature and the centering time, and the inert gas impingement, and the mechanical characterization with respect to the micro hardness, and the interstitial range and discussion. The next SEM analysis is also missing in some of the research work, and most of the research work are done as per just like a metal matrix composite, but FGM will be having a layer-wise deposition. Layer-wise deposition of the matrix and the reinforcement is to be extensively be visualized. Then only any person who wants to do research on functional graded metal can do and can be validated, right? Then if it is not validated, then research is of no use. It becomes null and void. And optimization parameters also not very well discussed. And the simulation of the FGM is also they have done a simple experimentation, or if done a simple analysis just like a cantilever beam or a simply supported beam. But to make a beam of FGM, it takes a more complexity. Only they have taken a 2D diagram, but that is not a research oriented problem. We need to discuss in depth. So this is my powder metallurgical process, that is the powder selection, blending, compaction, centering and metal characterization. And this is my, I have taken a number of matrix material here, only given the pure aluminum, not only the pure aluminum, alloys of aluminum. Basically I have done research in my doctoral level of this aluminum, because aluminum, everybody know, it is a light metal having high strength, high stiffness, low weight, and other high thermal conductivity, and low wear, and all kind of superficial properties with less cost and economical cost. So that's why I have chosen um, aluminum as my matrix material in the powdered form. Why? Because for the powder metallurgical technique, so compulsory, if you take an alloy also, we should convert into an powdered form. So not only the aluminum, pure aluminum, aluminum 356, aluminum 7075, and aluminum 2024. I have taken all the materials and I have done the research. So silicon carbide, titanium carbide, magnesium peroxide, uh, and all kind of ceramics, and all kind of brittle materials I have been considered, nickel. So to have the electrical properties, electrical conductivity, thermal conductivity, and magnetic conductivity, in order to have all kind of combined properties, I have taken all these properties. Next, powder metallurgy, it should be having then by using the compression testing machine, I will be producing the green compacts. So the green compacts are of low hardness. Then I will be making them into hard by using the centering furnace, that is the tubular furnace. In other words, also we can call it as a tubular furnace. And the tubular furnace, there is an provision of passing of the inert gases. Mainly I have taken argon gas. You can take an helium gas and neon gas depending upon the application. So research is going on in the uh, other kind of laser rays and other kind of gases. Why it should not be impinged on the products, and thereby we will be having the centering time, centering temperature, and the compaction pressure. These are the process parameters we have taken it. So basically our compaction process mainly depending upon our centering time and the centering temperature and the compaction pressure. That is the process parameter. But in the centering process, mainly it will be depending upon the centering temperature and the centering time. So I have taken from nearly from that is the what you call as the sound. Actually, the centering temperature, it should be the 80 percentage or 75, 70 to 80% of the melting temperature of the metal. So suppose if you take the melting temperature of the aluminum, it is 673 degrees centigrade. So then 70 to 80 percentage means maximum from 400 to 400 to 600 degrees centigrade we can keep our centering temperature, and the centering time is also very important. So and centering time, it will be cut off, and then it should be rapidly cooled. Until unless it is rapidly cooled, if you take then itself the specimen, then the specimens can be worn out, can be will be of no use when the characterization process will consider or will be take place. Next, I have taken layer wise deposition. Why? Because we need to have a layer wise gradation of the metal properties, either in the mechanical wise or in the microstructural wise or in the tribological wise or fatigue wise or strength wise or any other thing. So that's why I have taken a layer wise. So uh, why? Because I have only done for the 4 layers, means due to some manufacturing restrictions, what happen if I am going for 50 percentage of the silicon carbide and 50 percentage of the magnesium oxide, Then the metal becoming as a brittle material and couldn't able to get my part. Why? Because there is a lot of difference between the theory and the practical. So in the theory we can able to say that everything is possible, but in the practical, when you do the manufacturing process, when you do the compaction process, there is a lot of restrictions. So therefore maximum up to 4 layers I have produced. So then characterization involves all the things. Only here I have written only the tribological character, microstructural, mechanical, and I also conducted the Taguchi optimization. Because why? Because just by conducting the characterization process is not the sustainable goal development, but we should optimize the property. That itself suggests that how research is going on. So that is the Taguchi optimization I have done. So Taguchi optimization, that is the process of it, is an extensive thing. And also I have done the multivariate analysis. So why? Because there are multivariations, and then that is by done as the why? Because to identify the optimum parameters. Is there is an we should raise the compaction pressure or decrease of the compaction pressure, raise of the centering time or centering temperature, which is playing a vital role in the powder metallurgical process. So already I discussed, I have done not only the pure aluminum, I have taken 356, 7075, 2024, and all kind of alloys. And reinforcement silicon carbide, nickel, copper, titanium nitride, zirconia, magnesium oxide, aluminum, and all these are reinforcement I have considered due to their electrical thermal conductivities, and also to have high surface finish, microstructure, and fibrological properties. So we know that pure aluminum is having a density of 2.7 grams per centimeter cube, and reinforcement silicon carbide is having more than aluminum, 3.21. Magnesium is much more than, but it is of a brittle nature. That's why the bonding is low. But even though the density is high, the nickel is having higher density when compared to all these things. Zinc stearate, why I have chosen this zinc stearate is nothing but a binding agent. So binding agent is a one which will be combining the base metal and reinforcements. That is means it is acting like a lubricating agent. Why? Because if it is a lubricating agent is not done, that is silicon spray is also taken in another manner. If they are not taken, then there are chances they couldn't be able to bind. So therefore, they are susceptible to break. So that's fine. So these are the powders which I have taken in as a sample wise. So this is the layers. So layer wise. So this is the starting without means not taking the ball mill only. I have developed this kind of a box where we can put in the lathe check, and then we can have a uniform mixing of the blending of the materials rather than going for a this is a simple device I have done. So when keeping in the lathe check and then mixing thoroughly, why? Because these are powdered form, and the materials when we produce from the compaction process are having very low thickness. So just first basic thing what I have produced is just as the diameter as 15 mm and the height as 13 mm. So a very small pieces are produced. Why? Because that is an initial time of my research work. And then is also a computerized compaction process machine where we can have a higher compaction load and lower ejection load. Then these are the dies. So this is what I have proposed it, and I have also given the order for. I thought of manufacturing it by because to have my own product, I want to design my own compaction die and punch. So that's why this is the drawing I have drawn in AutoCAD. So this is the specimens I have produced. So this is the cylindrical FGM specimens of diameter 40 mm and thickness 10 mm I have produced. And these are the initial parts. This is the compaction and the ejection die. So this is nothing but the piston parts, sleeve and piston rods, also used as the what is called as the compaction of the material. And this anabond, that is nothing but silicon spray, it is used as a lubricant agent. This is the zinc stearate is also mixed with the materials to have non-breakage of the material, to have the less damage of it. So I have, these are also the specimens I have produced. And this is the compression testing machine. So this is the uh, characterization process I have done. This is the centering furnace. This is a tubular furnace. So upon this, I have seen that when there is an aluminum, and copper, the compression strength has been when the compression strength of an aluminum is generally 70 megapascals, it has been raised to a double of an amount. We are having nearly 140 megapascals. And similarly, also we can go for a 3 times then by using the silicon carbide and the magnesium oxide. So this is by the compression testing machine. So I found out these are the different one. So of the aluminum silicon carbide magnesium oxide combination, I am achieving an maximum one, and afterwards aluminum, titanium nitride, and zircon is also achieving the highest compression strength. So this is a Vickers hardness test. Vickers hardness test is also performing in higher number. And this is also my research work, and this is also hardness value. So the EDX, what is telling us the what you called as the chemical composition of it, no metal deformities. That is not metal deformities. Just no for no chemical reaction of the other compounds. No foreign materials and other things I have done. So this is the microstructure characterization of the topmost layer and the bottommost layer, and also this is an XRD analysis, XRD machine for the microstructure diameter of the bond, what is happening. So this is the tribological properties I have done in the tribological meter. So like this, I have done various kind of research. These are the graphs produced frictional force, wear, and also wear rate, and this is the coefficient of friction graphs. And so all other things I have done. This is the Taguchi optimization, and the Taguchi optimization. What I have done means compaction centering temperature is playing a vital role when compared to the compaction pressure and the centering time. So these are the 3D diagrams I have done. So also, so these are the applications of it, but not very extensively been given to the market. Only the research laboratories, the BMW and Audi cars uh, and latest researchers and latest companies, they have been doing in this thing, and why? Because they want to increase their market. So if it is made available to the market, ordinary person does the research, then it will be a loss to the company. So this is my end of my presentation. These are the different applications. This is my end of my presentation. These are the references what I have taken. And thank you so much. Any queries? Any queries from the participants? Any queries from the participants?
Thank you so much, sir, for this nice session. If has any question, you can ask. We will ask our participant to put your question in comment box. We will provide the answer. I think Mr. Srinivas sir. I think
Yes,
no
madam.
one has questions, sir.
Okay, madam.
Thank you so much, all the participants, for your active participation. Let me inform to all that this complete session will be available on our Research Circle YouTube channel. So if you want to watch it again or want to share it somebody, please to visit the Research Circle YouTube channel. Thanks. And last but not the least, thank you, Mr. Srinivas sir, for taking
Thank you very
your
much,
time
Madam
for
Sakshi,
such
Madam.
valuable
You are the backbone for this meeting, Madam. You have successfully conducted and made me motivated to present my research work.
Thank you, sir.
Thank you, Madam. Thank you.
I would like to end today's session here, sir. Thank you.